All right, can you guys hear? Cool. So my name is Constantine Nakos. I'm with the Qualitative Reasoning Group at Northwestern University, and I'm here to tell you about some of our work on debugging natural language systems. So before I start, two disclaimers. One, this is going to be work in progress. We've laid out the conceptual framework, we're working on the implementation, but we don't have any results to talk to you about yet. So stay tuned. Two is that this is going to be a high-level overview. There's too much nitty-gritty to fit into a 15-minute talk, so if you want to hear more, just go check out our paper. The motivation for this work is what we're terming hand-curated natural language systems. These are systems that rely on explicit linguistic knowledge for natural language understanding or generation, as distinguished from, for instance, neural network-based systems, where the knowledge is implicit and there's nobody in charge of debugging a specific problem. You might retrain it, you might try to improve, but you're not spot fixing individual bugs by changing knowledge. So the hand-curated systems have some advantages in that they are possible to inspect, extend, and debug. When something goes wrong, you actually can fix it. You can explain why the system is doing what it does. And the bug fixes tend to be incremental. Something's wrong with a particular word, you can fix that without retraining from scratch or worrying too much about the effects on other sentences. The problem is that these systems require a whole lot of expertise to maintain. The resources tend to be specialized for a particular system. There's different types of information that gets drawn in. It's not just text. And tracking down the errors can be difficult, even if you are well-versed in a particular system. Just the operation is complex. So how do we deal with this problem? Well, experts have a hard time debugging these systems. Non-experts can't even help. They don't know what a grammar rule is. They don't know the meaning representation, anything like that. So what we propose is a framework we're terming interactive natural language debugging. The idea is to debug a hand-curated natural language system by having it interact with the user in natural language. The user knows a lot about language and about the world, so they're a great source of intuitive information. The system does not know that stuff, but it does know its inner workings. So the idea is to bridge the gap between the two and have the system ask meaningful questions that let it access the user's expertise to debug itself. In a little more detail, we start with a sentence whose analysis is incorrect. How we find out it's incorrect, that's kind of another area of research. Given a sentence we have a problem with, we identify likely points of failure. We test them by asking the user questions, and we iterate this process until the error has been localized and corrected. The goals are to allow non-experts to debug natural language problems, to allow experts to focus on the more complicated problems that are harder to capture with this framework, and to facilitate lifelong learning through user interaction. So when you give somebody a language system, they can actually correct it by interacting with it as opposed to having to go back to the source. We have kind of broken this down into a 4-stage pipeline. We go into a little more detail about this in the paper, but at a high level. We start with a sentence that has a problem. The first step is trying to identify what the symptoms of that problem are. If we're supposed to get a complete parse tree for the sentence and we don't, that's the problem, that's the symptom. The next step is localization. The system will go back and forth with the user to try to figure out what error in its underlying knowledge is the source of that symptom. So in this case, it might be something like a missing grammar rule. We're just not covering that particular case, and the system can ask the user questions and try to drill down on what that grammar rule is. Once we have the diagnosis, we can then work with the user to correct the error And then once we have that repair, we can verify it to see if it clears up the original symptoms, to see if it causes any problems with other sentences, and ultimately accept it into the knowledge base. So a quick example that we're going to use as a kind of a running thing. Suppose our input sentence is Bob ate the wedge. Something I found out during my graduate career is that a wedge is a type of sandwich. I think it's a regional thing, but wedge can also be a golf club or a shape. So this may or may not be news to you. It was news to me. So suppose in this instance, the system knows about the golf club and the shape interpretations, but not the sandwich interpretations. Stage one is to identify the symptoms of the error. In this case, that would mean asking the user, what does wedge mean in this sentence? Does it mean golf club, shape, or none of the above? That gets us our symptom, that all the interpretations are incorrect. We then try to localize the error in the system's knowledge. So this can involve the user, it can involve internal reasoning, it kind of depends on the type of error. But if we kind of trace this back to the underlying knowledge, we find out that there's a sense of the word wedge that's missing. We can then correct the error by asking the user for the missing word sense. I'm making this sound a lot easier than it is, just because in our particular case, we're working with an explicit ontology and you have to make sure that everything plays nicely with that. But the user does have this information that can point you in the right direction. So here, the repair is that wedge can also mean sandwich. And finally, we verify the correction by making sure that the new interpretation of the sentence actually makes sense. A couple notes on INLD. One is that this is fairly idiosyncratic in that different errors are going to require different strategies. Sometimes you can just ask the user directly, is this the sense of the word wedge? Other times, you're talking about some distinction that's deep within the parser that might require paraphrasing the sentence or taking some other indirect approach. The main point is to translate the system internals into a natural language question that the user can actually render judgment on. Another point to note is that some errors are more difficult than others. Some of them are very much grounded in the system's internals and things that it has access to. Others depend heavily on the user and what the user knows either about the world or, in the worst case, the parser itself. We're trying to avoid that, but it's a little bit inevitable. If we have a complex grammar rule bug, then there's only so far that a non-expert user can take it. The good news, however, is that this is not an all or nothing process. Even if we can get partial information out of this, then that will point the experts in the right direction and ease maintainability quite a bit. I'm going to talk a little bit about how we're planning to implement this. But first, I need to give you guys a little bit of background on model-based diagnosis. The big idea is to use reasoning to identify discrepancies between an artifact and a model. So if you have a circuit that's malfunctioning and you have a model of that circuit, you can compare the model to the actual circuit and find out where the discrepancies are. Likewise, you can debug a student's misconceptions about physics by comparing it to your own model of how the problem is supposed to be solved. One of the systems that does this is the general diagnostic engine. This breaks down a device into a network of components, some of which are faulted. The diagnosis process involves taking measurements of inputs and outputs of the components. So you're testing these hypotheses by taking measurements. And the goal is to find a minimum set of faults that explain the observed behavior. We think this is a good fit for interactive natural language debugging. Specifically, this is a good way to formulate the identification and localization steps. And we'll get into that in a second. Now, if you're unfamiliar with GDE or just a little rusty, I'm going to go through a quick example. Suppose we have this circuit to handle a math problem. We have two multipliers on the left, we have an adder on the right, and the idea is to multiply the inputs and add the two products. In this case, we were doing 3 times 2 plus 2 times 3. The result should be 12. But suppose when we run the circuit, we actually get 10. The observed output is incorrect, which means we have a fault somewhere. Where is that fault? So what GDE does is it takes measurements of the multiplier outputs. In this case, suppose we get 6 for both of them, which means that the multipliers are functioning correctly. Because the adder has correct inputs and an incorrect output, we know that the adder is faulted, and we have diagnosed the problem. So we can apply the same thing to interactive natural language debugging. We start by automatically generating a model from a trace of the parser's behavior on a particular sentence. And the components are all of the elements of the parse. And by that, I mean just about everything. The syntactic constituents, the semantic expressions, the rules that are involved, the underlying knowledge, the knowledge base, anything that goes into the parse, up to and including intermediate processing steps. We just want to lay out all of the logic that went into producing the final result so that we can debug it. So in this case, we have the interpretations for wedge in our sample sentence. Wedge means golf club and wedge means shape. The inputs to these components are the previous steps in the parse, the constituents that help produce this part of the interpretation, the rules that gave rise to it, so on and so forth. And in order to drive reasoning about this, we add what we're calling completeness assumptions. These are components that explicitly encode the limits of the parser's knowledge. The idea here is that if the parser has understood the sentence correctly, then one of these inputs must be correct. It's kind of like a closed world assumption. So in this case, we encode the completeness assumption as a component with these two interpretations as the input. And the component is just a representation of the idea that all of the senses of the word wedge are known and present here. The values that get passed through the system are acceptability judgments. We use acceptability instead of correctness just because there might be elements that are suitable for another parse or otherwise not wrong that we don't want to cast any blame on that. So an element is acceptable if it's appropriate in the context of the sentence, and it's unacceptable otherwise. We measure these acceptability values by asking the user diagnostic questions, like we were talking about earlier. When we ask the user what senses the word wedge are applicable in this sentence, we get the answer that both of these are unacceptable. So we mark these with an X. It's green because for now, this is fine. We haven't derived any contradictions yet. However, part of this formulation is that completeness assumptions should be acceptable. If this completeness assumption is unacceptable, then it means that our interpretation is incorrect. So the output here should be a check, but because all of the inputs are unacceptable, the output also has to be unacceptable. It's like an OR gate. So because we have ruled out all of the inputs, we're now left with this issue that this completeness assumption is faulted. A faulty completeness assumption means that the system is missing the corresponding piece of knowledge. And therefore we can conclude that the system is missing a sense of the word wedge. And we've gotten through the localization step we talked about earlier. The research we're working on now is we are trying to implement this as part of the Companion's cognitive architecture. Our language system is the Companion's natural language understanding system, which is reliant on a bunch of different explicit language knowledge. It's a good place to apply this. We're using the Companion's dialogue agent for user interactions, and we're going to use an HTMS for implementing the general diagnostic engine. Our planned evaluation of this is to have non-expert users look for errors on a sample set of sentences and determine how often they agree when they derive an error through the system, how efficient debugging is, and figure out whether our error taxonomy is sufficient and whether we have the right debugging strategies. Before I wrap up, I'll touch on a little bit of a related work. Spiritually, this is very close to error mining, which is a technique for, is using statistical techniques to determine what n-grams are likely to be associated with a broken parse. So that is more corpus level and focused on highlighting likely sources of error as opposed to debugging specific errors. These two approaches are complementary, and in the future, we'd like to integrate them. INLD uses a very similar setup to interactive task learning, which is when systems are learning new tasks through instruction and demonstration. Some of these systems allow the user to extend the system's vocabulary as well. The main difference is that usually they are extending vocabulary for a specific task, whereas we're trying to use interaction to debug a general purpose language system. And finally, there's some similar work in the form of Kraken, which was a system for helping users expand the psych knowledge base, even if they're not necessarily familiar with the internals of psych. And that featured an interactive dialogue system that would help the user, walk the user through adding an entity by asking pertinent questions. So again, kind of a similar framework, but with a focus on general knowledge as opposed to debugging a language system. So to wrap up, we have observed that hand-curated natural language systems have attractive properties, but they are hard to maintain. We have proposed the interactive natural language debugging framework to help non-experts debug a natural language system by answering diagnostic questions. And we propose implementing the identification and localization steps as a model-based diagnosis problem. And we're working on building and testing this within the Companion's cognitive architecture. Thank you for listening.
Thank you for the talk. It's ambitious project. It's really exciting. So I have a question, and maybe it's you're already doing a lot, and so and this is kind of a bigger scope question. So sure. Maybe it's more philosophical, because language for humans is grounded in the world. Do you, and I think from the first diagram, you didn't have kind of a world simulator or anything.
No.
Do you think that with your system and the debugging, there might be limitations on what you could fix in the language without having like a state transition simulator or some kind of like world simulator?
Yeah, so all the stuff we've been looking at so far is language, quad language. Like it's, we're not worried about grounding this at all. In theory, kind of the same setup could apply to world knowledge as well. I'd be very interested to look into that and see if we could debug inferences, debug common sense, that type of thing, using a similar framework. But yeah, so far we're not looking at grounding, and this is just trying to build language systems that work better on the tasks we apply them to, as opposed to something that actually understands how the world works.
Hi. First of all, let me congratulate you on selecting a task, which is a very important task. Well, our team has been working on it for about like the last 25 years or so. And let me suggest that I really hope that you find some kind of a subset of the phenomena where you could get results, because with what you are describing, you will never get anywhere close to what you want to do. Why? Because on 3 counts. One is that the inventory of issues, inventory of problems that you can have with results of analysis is much more than word sense. And that's one. And second of all, the real question is, how do you support interaction with the system? Because you need to do deep language understanding, and then you need to have generation which is meaningful and not the GPT-3 type of nonsense. So it's like bears the question. So what you need to do, and I'm sorry for doing this plugin, read chapter 7 and parts of chapter 8 of the book called Linguistics for the Age of AI, which Mark McShane and I have published last year, MIT Press. You will find there some descriptions of some systems that we have already been doing. So, okay, pay attention.
Thanks. I'll definitely check that out. That kind of stuff has definitely been on my mind. In particular, some of the grammar rule bugs that crop up are very, very difficult. So we're going to focus on the stuff that's more routinized and tractable, and hopefully come up with some general approaches involving paraphrasing and stuff like that to help triangulate some of the more complex bugs, even if we can't actually address them fully. So hopefully we're going to bite off the right amount to chew.
I was just going to say, I think this is the last question for this speaker. If the next speaker wants to start getting ready.
I'm going to channel Emily Bender. What languages are you working on?
English.
So I think I think this is particularly compelling perhaps for documenting under-resourced languages where corpora and other automatic tools are not available.
That's a good idea.
But it, sort of means that you'll want to be working with the kinds of linguistic generalizations and like kind of, things like the resource grammars in HPSG have a lot of like kind of high-level rules that actually derive the particular senses that are used in particular parsers or grammar rules used in particular parsers, which is a kind of, I think, important challenge for this going forward.
Very cool. It's a good idea. Thanks.
Awesome. Well, let's thank the speaker.